Okay, I had to stop the recording earlier before I could get to number 25. So this is the very last question that was asked about on the Mod 3 review, and it's about a doubling time kind of problem. And it doesn't give you a specific amount of investment that was invested initially. It just says how long would it take for an investment to double at 14% compounded monthly and compounded continuously. So the reason it doesn't give you a specific investment is because all investments would actually double at the same rate. So it doesn't matter whether you're trying to start with $1 and double it to $2 or 5 million and double it to 10 million. It will take the same amount of time at the same rate, 14%, compounded in the same way. So that means you can either be real symbolic and you can just make up your own symbols for your starting and your final amount, or you can just come up with a really concrete number of your choosing. It won't matter. But the formula is a little bit different for each one of these. So this is something that you want to have in your notes. Hopefully you've done this problem already. This would have been from like 5.5's homework. But the formula is, in general, that's your final amount. This is your starting amount. This is sometimes called periodic interest because there's so many periods of time throughout 1 year that you're going to continue to do this calculation. So it's 1 plus your rate as a decimal, and then this is the new number. And I don't know, sometimes in some of the homework problems it'll call this S or N or other numbers, but this is the structure regardless of what letters we're using. It's always the interest rate as a decimal divided by this number N, which also shows up here in the exponent, where N is the number of calculations per year. So the number of times compounded per year. It's important that you understand what that is per year. That's a YR, per year, because you won't get it in a number, you'll get it in a word, the LY word, like monthly means there's 12 months in a year. So that means if we compound it every month over the course of 1 year, it will have been compounded 12 times. If it says quarterly, that means every 3 months or 4 times per year. So monthly means N is 12 in this case. If it said quarterly, N is 4. If it said weekly, N is 52, and so on like that. All right, so monthly means we're going to use an N value of 12. The rate, it said, was 14%, but we're going to use that as a decimal, so 0.14. And then the A naught, and then the A of T, that's just your beginning and ending amount. I'm just going to choose something easy. I'm just going to choose the initial amount's $100, and we're going to make it double to 200. It doesn't really matter what you use here, but as long as this is twice what you started with, because that's what doubling means. All right, so let me set up the formula with specific examples. I'm going to start it at $100. 1 plus my rate is 0.14. The number of times per year is 12. I'm trying to figure out the time, so that's why the T is here, 12 times T, and I have to set it equal to my desired output, which would be twice whatever I chose to start with. You can see why it really doesn't matter, because what's my very first step I'm going to do here? All of this is the base and exponent, so I need to divide that number out, and it's always going to divide and give me 2 in the very first step. So that's why it really doesn't matter with what numbers you start with, as long as you choose the second number to be bigger by twice of the first number. And then I am going to go ahead. I know I've preached before not to do any calculations in the middle, but for the sake of doing a base on a logarithm, I would like to go ahead and calculate this and put a decimal in here. The instructions said to round our final answers to 2 decimal places, so I'm going to make sure and write down a good 5 or 6 decimal places on this so that I will still have some accuracy for rounding purposes. So I'm going to do 1 plus 0.14 divided by 12, and I'm going to write that 1.011, and then we have just a repeating 6, so I'll do about 3 of those. So 1.011, and I'm going to write down 3 6s, and then the last one to round to 7. Okay, so I am just taking all of that in the calculator and getting a pretty good estimate. It's our final answer rounds to 2 decimal places, so that's why I want to use at least 6 or 7 places while I'm working in the middle here. All right, next thing is I want to get rid of my base, and that is when you apply a logarithm with that same matching base. I'm going to do that on my paper here. 1.011. How many sixes? How many 7? So log with that kind of crazy base decimal of 2. So you're always taking a logarithm of what you had on both sides equals, I can't believe I have to write this thing out twice. 1.01167 of 1.0116 to the 12t. All of that was so I can do this. Feels so good to work that out. Those cancel each other out because the bases match. That's how you get rid of a base. You apply a logarithm with the matching base. Okay, so now we're just left with on the right-hand side, that's what we wanted, something really simple to solve for, 12t. And I'm just going to copy all this down, and I will worry about working it out and getting a decimal estimate on the calculator later. So log with the base of 1.011667, log of 2 equals 12t. So I'm trying to solve for t, so I'm just going to, last step, divide both sides by 12. That's my exact answer for t. Now, it also asks us to compare it to the continuously compounding interest. So I'm assuming that we have to put something in here to get a decimal estimate so we can kind of compare a little easier. So let me go through here. Again, to get that log base, you want to hit the math button and then scroll way down, or I think it's actually faster if you hit the up button and look for log base. Type in the base, 1.0116667. That's my base. I'm taking the log of 2. Which, by the way, on these doubling time formulas, you'll always end up taking some kind of log of 2 because of this doubling thing. That this number is the answer you get when you divide out your final amount by your starting amount. All right, so that tells us that's the top part here. That all divided by 2, 59 something, and then divide that result by 12. All right, so it rounds to, it says round it to the nearest 2 decimal places. So 9798. So the 7 is the second decimal place, and it's followed by a 9. So the 7 is going to bump up. So to the 2 decimal place rounding, 4.98. So what this means is, again, whatever type of initial investment I have, if I've got something invested at 14% compounded monthly, it's going to take approximately almost 5 years for it to double. Okay, 4.98 years. So just shy of the 5th year. Okay, so that is compounded monthly. That's the more difficult, I think, formula to deal with because it has so many pieces to it. It's basically got like 1, 2, it's got $2 amounts, a rate, a number of times compounded per year, and a time. So it's got five different variables, and you have to plug in 4 of them to find the 5th one. So what we did here is we plugged in everything except t and eventually figured out what t was. Down here, 4.98 years. All right, it does say in the problem, the last thing it says on number 25 also, how long is it going to take at 14% compounded continuously for an investment to double? So I'm going to do that on another page and then we'll be done. Continuously is the one where you have E. So continuously would be kind of what that grows a little bit faster. The more little pieces that you end up breaking the interest rate into, so like monthly breaks it into 12 pieces, daily breaks it into 365 little pieces. The bigger you make that end number, the higher a result you're going to get. It won't be a lot, but it'll always be just a little bit bigger. So continuously is kind of like if you let that end value be infinity, be like doing it every second, but then 100 times per second times 100 forever. So it actually ends up approaching a simpler formula to use. That's where this E comes in. E has to do with that idea of increasing that in value to infinity. So you'll just have to trust me on this. You've seen it already in the homework, but again, these are starting and final dollar amounts or whatever it is that is growing in this way. But the E means continuous growth, continuous change. So we don't have to worry about an end value. So all of our other values are the same. So we can say we're starting it at $100. We're going to grow it to $200 or whatever 2 numbers you want here. E is a fixed number, so we don't have to substitute for it. The rate is still 14%, which I'm going to put as 0.14t. We're still solving for t, but we just have a fewer moving parts here. So same thing, the base and the exponent, save that for last. So divide the 100 on both sides. So we still get a 2. Remember I said anytime you're doing a doubling time problem, you're always going to end up taking a logarithm of 2 over here. And this is why, because when you divide the two amounts, it always comes out to 2. All right, now the next thing is I have gotten rid of everything but my base and exponent. So now the next thing is to get rid of the base. You get rid of the base by applying a logarithm with the matching base. And we've talked about this in some of the other problems I was doing for the review. E and natural log are inverse functions. Natural log is a base E logarithm. So those are going to cancel. So that means I need to go over here and apply a natural log of whatever's over there. So it'll be natural log of 2. So that means on my next step, when I simplify, all that stuff is gone, and all I have left is something times t. All right, so now all I have to do is divide both sides by the rate here, like that. And this is going to be, when I put this in my calculator and get an estimate, this will be how long it's going to take for any kind of original investment to double in value at 14% compounded continuously, which is where the E shows up. Now, because it should compound just a little bit faster. It should grow faster, so it should compound a little faster. So we should get a time value that's just a little bit lower than what we got on the other one when we're doing it monthly. Because if it grows faster, it won't take as long. So whatever it was, 4.98, I think it was on the other one. Yeah, there it is. So now we're going to do natural log of 2. We're going to divide that by the 0.14. And that gives us 4.95 rounded to 2 decimal places. Okay, so that makes sense that if it's compounded more frequently, which is what continuously is, and it would only take 4.95 years continuously. Okay, so continuously should grow a little faster. So it doubles a little bit faster, 4.95. It's not a lot, but technically it's just growing a little bit faster. And then the other one was 4.98 because we were doing it in a slower monthly compounding, which is a little bit slower. Okay, so that's number 25, a couple of examples of how to solve these interest rate problems. Always involves at some point taking a logarithm and usually dividing by something else to get to the final answer. Okay, so I will post this along with the ones from the other problems we were dealing with, and hopefully that helps you in your review. Okay.